So, Manvendra sir, you please start with introduction of the speaker with welcome speech.
Okay, so sure, sir.
Okay.
So, good afternoon, all of you. I am Manvendra Yadav, Assistant Professor in a Department of Mechanical Engineering, I.T.S Engineering College, Greater Noida. So, it gives me immense pleasure to welcome all of you in this webinar on the topic, the added values of innovation in advanced materials. So it is our also privilege that we have the internationally recognized eminent speaker, Dr. Mikhail Savajarvi from the Sweden. Yeah. So Dr. Mikhail Savajarvi sir is has been associated in material research since very beginning in 1995, and he started the many spin-off companies in 2005. He is an expert in commercialization of the commercial production of the graphene, and he is very key researcher in the field of materials. So materials research has its own importance. If we go in our history, our civilizations always affect with the material development. If we refer the Stone Age, if we refer the Steel Age, if we refer the Bronze Age, the materials gives the revolution in the human life, or you can say the entire world. Just few years back, no one can imagine the aluminum wire can be used in a electric motor winding or fans or AC compressor. But now we are using widely aluminum as a replacement of the copper wire. This happens due to the continuous innovation in the materials. So I can say there is always a room of innovation in the field of material. So before to proceed the webinar, I would like to give an outline of the session. So Dr. Sajarvi will share the knowledge on the ceramic materials, composites, material alliance, and more important, he will focus on the different field of materials research. So from our country, from our India, I feel again honored to welcome Dr. Mikhail Sajarvi from Sweden. Welcome, sir.
Thank you very much. So this is a great pleasure for me to be able to support your activities at this college, because we have earlier shared experiences and in the startups scene and other things. And certainly something which comes back, which you pointed out, is the innovations, and it's always a material issue with everything which comes back. And today I will share some experiences from the how opportunities emerge from the advanced materials, and also in different disciplines, so they can go from semiconductors to other disciplines over time when there are new findings, but also more people who are involved. And when you meet people, that creates opportunities. So today I will share some of my experience, and as was pointed out here, I have been active quite many years. So I started with the research in 1995, so that's quite a number of years now. So I will show you, and I welcome all, particularly all students who are here, because those are the ones who will take the findings and create possibilities for the next steps. So now I will show you, because I started as a student. Can you see this? So this, as I mentioned, I started as a student in applied physics and electrical engineering, 1989. And the tradition in Sweden is that when you start a new program, then you have this type of overall which is used for the celebrations and so on. So when I was young, this was the size of my student overall. So, and since that time I have been growing. So this is a traditional history. But I started as a student in 1989 on applied physics and electrical engineering. So this was my interest when I got started with different things. And at that time, I did not know exactly what I wanted to do. I did not have a plan for what will happen and so on. I just started this program and then came into the research because that was one of the interests. So what I will now share with you is that when I started with the research, I came into the silicon carbide. And in this slide, you can see the basic principle of silicon carbide. And this is basically that you have a source material which you heat up, and then you have vapor species which are formed. And they are then transported to a growing material. And with time, that material will grow larger and larger. And in the 90s, it was a big interest emerging in silicon carbide for power electronics. And like in Sweden and many parts of the world, there was a big program. So it was a lot of activity. So that's how I got involved into the growth of advanced materials. And my particular focus is silicon carbide. And the aim of this research is that there will be wafers which are produced. So this is a wafer. This is an example of silicon, but basically silicon carbide will also be developed from the material growth to wafers. And over time, there have been improvement in the growth, and there have been device improvements, and people started to understand the device properties of the material. But it took quite many years before it became a real market. So it was only just a few years ago when silicon carbide became a market, which is where there is more money being possible. So that took more than 20 years before the silicon carbide came into a market. So I'm not involved in the market, but this is the basic process which was used to get material for that. So that's a background of these things. And my particular focus in growth of silicon carbide was to modify this method and change the conditions so we had a smaller distance for the transport of material. So then we cannot grow large bulk type material for wafers, but we could grow thick layers. So that was, and then the idea was that that is interesting for the power devices, because then you need thick layers to transform 10,000 volt and so on. So in my PhD thesis work, we have been using as source material, we use this ceramic silicon carbide. So if you look at the bottom here, where it says source, that is a polycrystalline ceramic material, which is available and being used in the industry as a dummy wafer for thermal properties and for high temperature properties, because this is what silicon carbide is good for. So then we are sort of into the ceramics, but we are using this for the electronics thin film growth. So this is available so I will come back to this ceramic type of silicon carbide when I talk about the new applications which emerged from this. But just to complete the story of my PhD, here we have a wafer, small wafer, with a silicon carbide thin film on it, or for silicon carbide it was a thick film. So that was a good achievement in the growth. But it turned out that this layer was not suitable for the power devices because it was not pure enough. So it was not possible to use this for its intended purpose at that time. So the highlight of my PhD thesis was a process for making material which was not useful. So that was 1999. And then a few years later came this guy from Japan. So Professor Satoshi Kamiyama from Meiji University, he presented, oh, I would like to use silicon carbide, and I don't care about the purity because I want to introduce certain elements to dope it. And then there will be light coming out from the silicon carbide. So suddenly that became a new research field because it was not a traditional one, because the traditional field was for silicon carbide for power devices. But then came this guy, and what he needed was a process for making thick films. So then I had, oh, I have a method for you. So then this process became interesting again for a new research field. So that was when an innovation from this Japanese researcher who came into, brought us into a new avenue. It was not planned or anything like that, so it just emerged. And so then we started this collaboration with Professor Kamiyama on silicon carbide for white light LEDs. That was very nice, and also it increased the network, and we started this collaboration with the team there in Japan, and we had a collaboration with Denmark and Germany. So my personal network was initiated and started to grow. So this was a few years later, 2010, and here you can also see Professor Kamiyama on the right side there next to me, and next to Professor Kamiyama you have Professor Isamu Akasaki, and that group got the Nobel Prize for the blue LED. So then we started to have exchange with the very distinguished research groups. I was super happy because I'm a simple guy, and we started to have this collaboration, but it was due to the materials which emerged into a new innovation avenue. And of course, like with all innovations which come from material, it takes a long time before it's a device or in the market. Like I mentioned, the silicon carbide started from 1990s, and after more than 20 years it became a market. And if you look into the blue LED, which is now used for making the white LED, because you have the blue LED and the phosphor, and then you convert the blue into the other colors and you have the white LED. But the materials research started in 70s, 80s, and then 1993 you had the blue LED commercialized, and then maybe 15 years later you had the white LED. So also this innovation from the LEDs, white LED, took many years. So whatever we do when we start from the materials, and the examples which Professor Yadav gave now, that they need to find their applications and markets, and sometimes everything is just shifted to other opportunities than the ones which was the initial idea. So here we have this collaboration with the Denmark High O at Denmark Technical University, who are now continuing this development for white LEDs in collaboration with Japan and China. But that's one example how an innovation and materials expertise came into a new avenue. And of course, I'm not doing the experiments in the lab since a number of years because I tried to find funding for these projects and so on. So we have people in the lab who are doing these things. So the students are the most important because they do the actual work for these research fields. So here we have Valdas Jokubavicius, who started with a PhD student with me 2010 in the fluorescent silicon carbide for the white LED, but also in the cubic silicon carbide. So for the power devices, there is a field of particular silicon carbide format, a polytype, which is called hexagonal silicon carbide. So that is the one which is recognized for the market and so on. And silicon carbide can be made, it is built from the silicon and carbon atoms. So you build it and then you have different types of silicon carbide. So there's maybe 200 different versions, and there's one which is very mature. But then you have the little brother in the silicon carbide family, which is called cubic silicon carbide. So this has traditionally been very difficult to grow because there are more challenges in this process for the growth of this material. But this is what Valdas came into, and during the years it has only been possible to grow very, very small pieces of cubic silicon carbide to control the growth and so on. So that has been many research groups which have explored these things. But what we succeeded with was to control the growth in a little bit better way. So these small crystals, they were a little bit larger and larger over the time. And then we started to have larger grains. And this also means that then we have better quality of the material. So that's how we came into the cubic silicon carbide. And then I was I really like to give presentations and discuss these things because then you meet new people. So some years ago, I was at a conference talking about the fluorescent silicon carbide. And then I went to my seat, and then came the next speaker. And he was talking about intermediate band gap. So this is for solar cells. So when you have the electronic band gap, if you insert a level here, and you have a particular values of these ones, you can collect more from the solar energy in one material. And then it turned out that this cubic silicon carbide fits very nice into this model, and we can dope it with certain elements. So then we came into an avenue of solar cells from the cubic silicon carbide. So that was another new avenue from innovations where you met people from other disciplines. They were talking, and then we had our results, and then we, in some way, we found a link. And then highly efficient solar cells could be possible from the cubic, but also the properties are interesting for conversion of water using solar energy to hydrogen using this material. So that's another research avenue which emerged from the growth. So these are a couple of examples which we came into from the materials point of view. And always when we have activities and there are new approaches, then the material properties and understanding will always be important. When you come to the device and so on, device people will ask you, what are the properties of this material, or do you know it, and so on. And sometimes we don't know anything, and then we need to explore it and modify the growth. So it's like circles of iteration of information, but it always comes back to the material. So that is an issue. And then one day I got a phone call. There was a guy working with sensors for engines. So he said that, oh, I have this idea. It's a sensor, a pressure sensor. So if you have this membrane, which you put close to the engine, and when the engine is working, it can detect the pressure changes. So if here in the center, where you see the silicon carbide membrane, this part, this is a cavity between two plates. And when it's in contact, facing the engine combustion, it changes the cavity. And this is detected by optical means. So this guy said that, oh, I'm very interested in this silicon carbide membrane, so we need two plates to join each other. And the motivation here is that when you apply this in a car engine or a lorry engine or other engines, you can go to higher temperatures and you can save fuel. And there are some estimations saying that 1 or 2 or 5%, up to 5% of fuel can be saved using this optical sensor or gas pressure sensor. But here, when we were doing these types of growth, when we had two pieces close to each other, we were transporting material. But sometimes they got in close contact with each other and got stuck. And that was an accident in the growth. But then we had two plates in contact with each other and they were impossible to remove. So I tried with knife and different things to remove these ones. So in the growth, at that time, it was a mistake. But now, this guy wants two pieces together with a cavity inside, and it must be in contact because it should be no gas leaks from the engine to the detector part. So suddenly we came into a research avenue about using two pieces of silicon carbide towards each other, and then the mechanical properties are super important. So the bonding strength and all these things which became, so that's became a new avenue for us in this research. So now we are initiating this. And I don't remember how we got contact first, but maybe he was reading about our silicon carbide activities, because I've always tried to be visible with our activities. And then he called me, "Hello, Michael, I have an idea." And then I said, "Oh yes, this is very good." And then we came into that avenue. And further on, in that avenue, we have the membrane. So this is the silicon carbide part. But this should be put into an engine using a housing, which should be either some ceramics or metallic alloys. Like in an engine, you have many metallic alloy parts doing the different things. And when they modify the engines to be more efficient, you modify geometries and working temperatures, but also the materials inside. So here we need silicon carbide in contact with a metallic alloy, which should be in contact with other metallic materials. And then the mechanical properties, and in an engine, when you have combustion and when you go to higher temperatures, there's a lot of vibrations. And also, these things must last many years, because otherwise people will complain on the cars that the sensor is not working or there's some problem. So the mechanical properties in this type of new avenue are really important. And of course, I don't know anything about the mechanical properties related to this, because I come from the silicon carbide growth of the material, starting from the electronics for using semiconductors, and then we came into other avenues for optoelectronics, and now we suddenly come into this part where we merge two pieces of silicon carbide, and one of them should be ceramic and one single crystal, so that should be the main part. So the ceramic silicon carbide is now again used in this type of new avenue. And then the mechanical properties are the ones which are the important, because these must last. If you buy a car, you want it to last for maybe 20 years without major issues in how the fuel is used. And now in Europe, there's a big driving force to reduce the fuel used in shipping. So until year 2050, it should be reduced by 50%. So European Commission and all actors are now trying to find ways how can we reduce the fuel in these big engines. And then also this sensor can be important because it can handle the environments, but it can measure also very fast with a larger bandwidth and so on. So there are also very good motivations for using this type of sensor in the shipping. And do you know that I think it's about 3.5 million barrels of oil which is used in shipping every day. So if we would be able to contribute to save 1 or 2% of that, it would be really fantastic. So this is a new avenue which emerged, and now we try to initiate this in the growth of the material and of the membrane, and next we will start to measure the mechanical properties in this type of membrane. So if you have any ideas how we can collaborate on such type of mechanical properties and testing towards new avenues for these things, I'm very interested. I'm initiating these projects now, and in Sweden we need funding for activities, and also in research the salaries are paid from the funding, so we need projects. But I have a lot of experience with India since before, so we have some ideas already there. So I also hope that this could be an opportunity when we have a Sweden-India webinar just to exchange experiences. I can also give another example about where the mechanical properties become the most crucial thing. We also work with with graphene on silicon carbide. So when we have the silicon carbide and when we heat it up, we have silicon and carbon. And when there's more silicon lost, then we have a carbon layer on top, and that is graphene on silicon carbide. So that's how we came into the graphene on silicon carbide many years ago. And before that one, when we were growing silicon carbide and when we failed ultimately, then we graphitized the surface by this process. And now we start to control it since 15 years to have one layer of carbon. But that's how we came into the graphene. And then there are also other types of graphene, like in the flakes and so on. And I have a colleague who is working with graphene oxide. And he initiated thoughts about that you can use the graphene for antibacterial purposes. And then this is a picture of a graphene flake. So it's very, very small. But the graphene is not perfect in this type of flakes because it's slightly not planar. But you also see that it's not symmetric shape. It has a little bit different edges and so on. So actually in this antibacterial function, it is these edges which kills the bacteria or makes them problem. So it's not a chemical reaction of the graphene, it is mechanical. So this is another avenue where the innovation came into new use, like in this case. So that's just an example. So we are actually now initiating, we have a project proposal between Sweden and India in another collaboration in this aspect. That's why I'm talking about this. And one of my colleagues is working with the material, and in India there is this activity for antibacterial surface coatings and so on. So that's how I came into this avenue. But originally The material growth had some findings, and then you find other applications which were not intended from the beginning. And it's not the electronics or the chemistry things, it can be also the mechanical ones which are the most important, and maybe that's the one which makes a business case. And these were some examples where I have been involved and have seen some things, and over the years, when I'm no longer in the lab doing experiments and so on, then I meet more people, and that's why I'm also happy to give presentations or interact with the community in different ways in research, but also the startup seminars which we have had. Then you exchange information, and then people talk about different things, and then you come into new possible projects. So I think if we are doing more of those things, having discussion, sharing experiences about this is how I did, and this is how I came into this one, so then maybe other people can have use of the learnings, maybe not the whole, but maybe a part of these ones. So you can use this as an example for your own case. When you have an innovation, then you can take it one more step. So the exchange between the people is very important in order to realize the technical ideas and so on. And several times I have seen that when the idea has been this one, it has been this part which became the application and market and business. And this emerged from the meeting people. So this is just a simple sketch showing that if we have groups and teams or activities with competencies, if we are sharing these things, we can create more opportunities. And like now, with these ideas which are now coming, you cannot have the idea and just do it regionally in your region, because if it's a bigger idea for a bigger purpose, it immediately becomes international. And then you will not have the value chain in your neighborhood. You need to meet other people either in the same country or internationally. So this exchange is needed to make the value chain for an innovation. And then different types of disciplines are needed. You need maybe people with electronics, but also mechanical, to work together so you can understand the full concept. For example, like in this case with the pressure sensor, this is just a detecting mechanism, but then you should have electronics handling all these things, and then the electronics should be communicating with the other parts of the car, and then also in the system, so you optimize the whole system. So then you can also come into the how you use artificial intelligence to handle all this data, because maybe the cars, the engines will communicate with the full society when they're traveling. So that's how I can envision the future to evolve from the ideas which we have. But everything starts from small ideas which we have, and you don't know if that is successful or not, but one should try if one believes in that, because the future is, there is so much, so I'll stop, yeah, there I found it. So, that was my experience from my original experience from the semiconductors, and then we came to other avenues, and then now recently we have this membrane project where the mechanical properties become important. And maybe all my learnings over the years was intended for this part. I don't know, maybe or maybe not. So with this, I would like to give an example that we don't know what things will be useful for the future applications or the society and so on. But continuously to work on these things is important. And then it's important that we, and especially if you're a student, when you have ideas, continue to try them, even if some professors sometimes says, oh, I tried that many years ago, it did not work out. But everything comes into a new perspective when there's new findings and new applications, like this LED for silicon carbide. It was not, many years ago, it was not known. So I encourage to continue to work for those things which you think are interesting and believe in.
Dr. Mikhail, many of the participants also want to hear from you how to commercialize the startup, means how to commercialize the research. Basically, they want to hear from you some techniques behind the commercialization.
Yes, so there is no recipe. That's why I talk about this sharing experiences. That if I tell, for example, with the graphene, what we made, we had a research finding in the lab, and then we had a patent on this one, but we could not afford to buy an own machine for a company. So what we did was to rent the equipment in the research lab every Monday for the company purposes. So then we did not need to find the money for own equipment. And then we could have activities to start looking for customers instead of trying to find money for the equipment. So these are some things which you can do when you share experiences. This is how I did it. Maybe it's useful for someone or maybe not. But if everyone does this, then we share ideas, and then people, after some time, maybe you find opportunity. But one of the most important for me is always to find work in a team, because if there's one person doing the invention and so on, there's so many business things and then maybe some legal aspects and economics, so then it's too much for one person. So always try to work together in a team. When you have an idea, find a partner, and that should be based on very good personal chemistry, because this will take many years to do. And then together you will find different ways of how to get support for this idea. And like we have been trying to do, is that to use the research money as much as possible to make it as mature as possible in the research before the next step. So then we can use the soft money for maturing it as much as possible in the research, and then some other money before investors and so on. So that is, try to make it mature, but then also be very active to meet people, because maybe you need something, but you don't know who you will ask. But if you go to some event where there's a discussion of startups or regional growth, then maybe you meet a suitable person for your case. So this networking is one of the basic features which will give possibilities either now or later.
Oh, thank you, sir. So I request the participant who joined our this webinar to proceed for the question and answer session. So you can ask the question to the speaker.
Yes, and I see also in the chat question and answers, there's one from Vashu Panvar. So the question is how remote communications technologies impact the need of people in the future. I think these remote communications will happen because then there is like artificial intelligence and things which are come into play, and we want less control, less people to control the things, because the more you can do with artificial intelligence or digitalization and all these things, then more you can achieve with those things, and then people become available for other things. So I think that these remote communications and technologies, they will not be a problem for people, because then they will release that you can spend time on doing other things which are add-ons to a technology. Some people are scared that the robots will take over and so on, but I think this is a way just to release more, that you can possibility for yourself, for people to work with other things which are next steps. And many of these things which are relevant, it's personal chemistries and so on, which robots can not have that. So it's people doing people with other people, doing business with other people. So that is.
Thank you, sir. So next question, I think from the Ravindra Ram.
Yes, I have, in my screen there is Bhupesh Oya has, please suggest some applications on silicon carbide power. So, and in that one I think that, like you have now the 3D printing and additive manufacturing coming in. So I think one can use the silicon carbide powder and do 3D printing of silicon carbide for new applications, and then most probably it would be more related to mechanical properties, and maybe that is something which we can explore for these sensor applications, when we combine powder into solid materials and then maybe combine it with the metallic alloys for transport applications and so on. So, and there maybe the benefit is silicon carbide and some certain metallic alloys, they are more useful for higher temperatures. So that's the competitive advantage. So that I think is one idea for silicon carbide powder. And there's a next question here is Akash Bhatti. In today's scenario, what is the motto of research in the field of smart material? Okay, motive.
He's an undergraduate student, so he wants to know the future. He is worried about his future.
Yes, so I think one motive is that it should solve some particular problems. When we read about properties of material like graphene and other ones, maybe we imagine that this is good for those things. But maybe when we are in contact with the industry and so on, they will tell, oh no, that's not our interest, we are interested in this. And then from knowing that, we can address smart materials towards that avenue. So that is one of the future. We should not believe without having some feedback from where someone wants to have this smart material. So smart materials can be smart, but they are not useful. So make it useful and then add on the smart properties. This is my thinking of motive of research. So this is also again coming back to interacting with the society, industry and other people, not only the researchers, but find other disciplines where they see that they will say that this is important for us and so on. And then there's one question about power reduction or reducing size of components of artificial modules. And that is, I'm sure that is important, and the more we go to things which are lighter and should use less energy, it doesn't need to be fossil fuels, it can also be batteries and so on, and then we reduce the batteries we can reduce the batteries if there is reduced sizes, and if there's a reduced power need, then everything goes together. So this reduction of power and reducing size are linked. And of course, all those different parts will communicate with each other in some artificial way. So it will be, like the question is artificial modules. So it will be such type of modules in some way, which I imagine. And there's a question about from Madame Mohan Puram. What is the maximum temperature that cubic silicon carbide can withstand? Silicon carbide can go to well above 1200 degrees without anything happening. You have maybe some lateral expansion, but at 1500 to 2000 degrees C, depending on the pressure, it starts to sublime. So you have material leaving the surface. Then it starts to degrade. But basically, more than 1000 degrees C, then it's not much is happening from the mechanical properties. So that's why I think that the cubic silicon carbide, but also the ceramic silicon carbide, and also if we do additive manufacturing of silicon carbide, it will withstand high temperatures once it has been processed for that. Many questions. It's very good, so I will be sitting here all day. I had the day off for this, so it's no problem. So Harsh Gupta has a question about how smart materials can be accessible to common man. I think we will see these things in the shops and so on, but we maybe don't realize it. So common man will see these things built in. For example, already today, if you buy a car, it has a lot of interactions in different ways which you don't see, experience, but it functions. So they are basically accessible today, and there will be more in the future once there are more functions and materials. And in the future, there will be combinations of materials with each other to even broaden all these things. But most things we will not see unless we are in the research of these things. And then we have a question from Said Asif. Can materials fine visualization do through conventional neural networks also? I'm not sure I understand the question, but maybe it's related to neural networks and materials. So if we can visualize the materials in them, then it can be useful. So I think certainly the more we understand from the fine parts of the material, so when we visualize it either by measurements or simulation, then we understand them also in other applications. So also neural networks, they are built of small parts of the material and which communicate and do this, send these pulses. But it's materials which are used for sending the pulses, either electronic or some other ones. And here's a question from Nidhi Sharma. How do I know my idea is good? I think you don't know if it's good, but if you like it, you continue to explore it. When I started, when I got into this silicon carbide for white LED, then people in the semiconductor said that, no, it's not possible. You know, silicon carbide, it has this property of indirect band gap. Then you cannot make it an efficient luminescent material. Like nitride, it has a direct band gap. That's why it can be efficient. But silicon carbide does not have a direct band gap. That's what most people said. But the mechanism is not that it needs the direct band gap, because it's another mechanism for creating the light in the silicon carbide. So people told me that my idea is not good due to this, but they did not know everything. So if you like your idea and you believe in it, continue to explore it until you yourself find out that this is good or not good. And it doesn't mean that it's not good, because maybe in the future it might find maybe it's not good now, but a few years later it might be very good when it comes to a new situation, new application or something. So my general recommendation is that if you like your idea and these things, continue to do the idea, and then you have a lot of fun on the way anyway. So there's no way to know if the idea is good, because it might find its purpose in some other unexpected way. And then we have a question here: what are the recent advances in ceramic materials regarding their use in automobile industry? I'm not so expert in the ceramic materials and automobile industry, because we are in the emerging things. But basically, when I have been meeting people in our region, when we talk about how should the region continue to expand and what can we focus on, then we have composites and ceramic materials as an activity. So I think what will happen in the ceramic materials is that there will be more properties when you combine different things, and you can maybe use it not only for the mechanical strength but also send signals, electric signals, so it has more properties in one type of material. And like there, when you talk about graphene, it is used in other materials, and you add on the graphene into other materials, and then you add some properties. So then that original material got little more opportunities due to the combination with other materials. So I think this is the same for ceramic materials. When you combine different things or find new ways to make them, you can make advances, and then the lightweight and fuel savings and so on will be part of it, but also the communication and sensors integration and so on. And then a question from Bhupesh Oya. Material challenges to store energy in e-vehicles. Yes, I think there are like batteries and how to store the energy in different ways, but also maybe you can in the future you can store hydrogen and use that as for creating the energy. And just recently I came into contact with a network where they have an idea, and it was also from India, to make a hydrogen vessel by additive manufacturing, and then you can make any shape and so on. So if that works out, you can have a portable hydrogen storage vessel, and maybe for e-vehicles and so on. So then there are ideas about material challenges related to additive manufacturing for such composites and so on. So there will be, but you need to store the energy in some ways and keep it safe and make it lightweight, because these e-vehicles, they should use as little energy as possible. So there are many challenges to be faced. Here's a question from Koshagra Goyal. How to clean LPCVD quartz tube after 3C deposition? We did not have so much problems, but originally in the CVD growth, it was done by HF acid etching of the quartz tubes. So that was one way how to clean the deposition in the quartz tubes. And then later on, what we did, and also the collaboration partners in the research division, we did not clean the quartz tubes as much, because now it is more common, so you can actually buy a new one. But in the CVD, it's more expensive, of course, and so then maybe cleaning is one way. But it was such type of cleaning. I'm not an expert, because we were not doing the CVD. We used the sublimation process, but that's how I remember it was done before. In our case, we could remove deposition by going to high temperature because we use higher temperature in our process than the CVD. And then Kushagra Goyal asked, how can we differentiate silicon phase and carbon phase of silicon carbide? This cannot be done by directly watching it, but after etching, they had different etching character, and also the oxidation character are different for the silicon phase and carbon phase. And so usually etching by KOH is done to differentiate silicon phase and carbon phase because they behave differently to the etching. Chetan Dixit asks how smart materials can be joined. Very general question, but I think when you have an idea about your smart material, if you meet other people with their smart material, if you discuss and have exchange, you will find a way, this is how it could be done. Or maybe you find out, no, it could not be, but what if we do like this? Then maybe it matches. So then you join materials in different ways, but they need to have some natural matching from chemistry point of view in order to make it realistic. And then there's a question, does this material will bring changes in the automobile industry on the basis of profit? I think the materials will make it make more possibilities, but there's always this profit. If the industry does not see the economic benefit of the material, it's very difficult to get them to use these, and maybe they will even oppose you if you have an idea which is technically better, but you cannot make profit. So the profit needs to be in alignment with the technical advantages. And maybe sometimes we don't see the profit because it is not volume profit, but there are some profits in where there is not the money which makes the value. And we have the example of sustainability, because companies now need to show that they are doing things which are for the sustainability, and then the economics cannot be the main motivation. They need to show these ones. Then it's a sustainability profit, which is also comes into play of the materials. Many questions here. It's happy. So next question is from Ashirvad Pal. How can I determine that I'm capable of doing a startup or business? And basically, if you want to do it, then you do it. And when you have limitations in something, you partnership with someone who has, for example, I'm not very good at calculating the financials and making those type of tables. But there are business people who are doing those things. So if you find a nice partnership, then those people can take care of that, and I focus on what I'm good at. So I think everyone is capable of making a startup or business. Maybe it will just not be successful, but it doesn't mean that it's due to you as a person. It can be politics or things which makes things to disappear. Or now, like when we have an example from the COVID-19, there are many startups which have big problems because everything just changed, but it's not due to their original idea or them as persons. So everyone can make a startup, and then sometimes you are very lucky, sometimes, or usually, one is not so lucky, so you manage in a short time. It will take many years. So in general, I think the recommendation is to try to have patience with these things, make a plan which is not limiting you too much. So you need to make a decision. If you're a little more relaxed with things and make a little bit longer term, then opportunities will emerge in a startup. Oh, here is a question which I'm not good at answering because I don't watch movies. I play guitar and music. This is my, instead of watching TV. But the question is from Akash Bhatti. Suit of Iron Man, which is using nanoparticles, is it possible to build or not? I'm sure it's possible to build, maybe not with all these properties like Iron Man and so on, but now there are nanoparticles on the surfaces, and I got into contact with one guy from US where they modified the surfaces of materials according to the butterfly, because you have irregular surface and you can collect more energy. So it is certainly possible, and I think there will be many benefits when we make the first the traditional material, but then modify the surfaces for additional functions in addition. So maybe not Iron Man yet, but certainly there is possibility to make use nanoparticles for building things. And then question from Manas, can we 3D print these materials and composites? It is possible to 3D print most things, but one of the challenges is that it should maintain the properties which are desired. And if you 3D print, there is still surfaces, they need to be modified or polished in some way to be able to be useful. So the 3D printing is only the first step of any material, and many can be printed, maybe not in the quality or purpose which you were thinking of, but then maybe they will find another avenue. And then it also depends on the 3D printing techniques. But for example, this US guy, he had another 3D printing, not layer by layer, but when you have a certain polymer and when you have light shining from the different geometries, you can make a shape from the energy of the light into this polymer. So then you're 3D printing in other ways. So it's not only the layer by layer, which is traditional, but there are also other ways, and I'm sure that there will be other possibilities to make even more 3D printing versions, and then more materials and composites come into the play. And then we have Mohit Kumar. What are the advanced materials? Some examples. Basically, advanced materials is traditional materials which have new properties. And we can take silicon as an example. Silicon is now used in our laptops for the processors and integrated circuits and so on. So then they already have a function. But then when you modify those in different ways, for example with nano patterning or combination with nanomaterials on the surfaces, then it becomes even next step advanced materials. So silicon combined with other things, but another advanced material is the carbon. You have the graphite, carbon nanotube, carbon in different ways. Carbon is in diamond. So those materials which we have heard about, they are advanced, but maybe we cannot use their properties yet because we don't know how to use them. So it doesn't need to be super exotic new materials. Advanced materials can also be the traditional materials, but we just need to use them in new ways. Then we have a question from Said Asif. Can we make a material COVID disease free? Yeah, I'm sure of that, because these bacteria and viruses, they don't like any material. There are certain materials which they don't integrate with, and then they cannot live on them. So then it can be made COVID disease free from the material properties. And there I would guess, I'm not expert in that, but I would guess that, for example, like metallic materials, this is not very useful for bacteria and so on. They cannot grow on such type of inorganic materials. So that's my just an idea. I'm not in this field, so difficult for me to answer with detail. And then Prab Simranjit Singh is asking, what is the energy band gap in silicon carbide? In the power device material, which is now for used in the market, this is the 4H silicon carbide. Then the band gap is 3.3 electron volts. And then you have hexagonal 6H, which is 3.0 electron volts. And then the cubic silicon carbide, this has a band gap of 2.3 electron volts. So it's a difference to these ones. That's why it has a certain attraction to different applications like solar energy, but also like conversion of medium power. Then the band gap is more suitable in cubic silicon carbide than the hexagonal ones. But we cannot make this material in good enough quality and so on. So 2.3 electron volts and 3.3 electron volts are the most common ones in the. And then also a question from Vasiuddin. Can material, is it useful for surface grinding? Unlike silicon carbide, this is already used since 150 years or more than 100 years ago for grinding and polishing. And if you buy polishing paper, this is made of either diamond or can be silicon carbide, small particles. So there is a process of silicon carbide when you heat it up with silicon and carbon in different ways. You get powder type of material which you add on to surfaces for grinding and polishing. So that has been done 100 years already. So the electronics is more difficult because then you need better quality. But here the mechanical properties are used for silicon carbide. Ravindra Ram, how the properties in smart materials is retained during the application, and how the life of smart materials is found out. This is an important question for long-term stability. That's why, for example, this sensor which I was talking about, when you calibrate that sensor in the beginning, then the engine has certain function. But over time, engine is degraded and there are depositions, and so all the conditions are changing over time. So then, if the material can adapt to such situation, then it's useful. And depending on application, it's difficult to know which properties. But for example, if you can heat this one up, so so the material does not interact with the environment more than for its intended purpose, then such properties are interesting. And then the lifetime will be related to that one, and then to actually see what is the lifetime of a material, then you need experimental. You can do some simulations and so on, but it's very difficult to find out in some cases. Like our fluorescent silicon carbide for white LED. The traditional blue LED with phosphor, the phosphor does not like heat, so it degrades. So that's why you see the white LED of today, it shifts a little bit in tone, especially when it's warm. So this is due to phosphor changing its properties. But like in our case, the silicon carbide, we don't have same type of phosphor. The silicon carbide is acting as a phosphor, and then it's a semiconductor material and it doesn't degrade. So then the estimated lifetime is 35 years. But it's difficult for us to measure and so on. So I think estimations can be done in certain cases, and then otherwise you need some stress testing, or if you go to higher temperatures just to estimate it, then you use certain stressed conditions to find out if it's realistic to be long live or not.
Manvendra sir, I think we should conclude it now. Huh? It's too long.
Hello. I think the questions are mostly on any material that can never break. I think one more question you can give the answer.
In the next question here, there's a from Bhupesh Oya. If there is any platform so we can have guidance, get guidance for research activities. And this is what I'm trying to initiate now, like with the Sweden-India exchange, to make a platform between activities for sharing experiences. So it's not only my experience, but there are also other people who have this experience. And when we meet, we can get... So I'm now trying to establish a platform for exchange and innovations. And then I think one way there is that we can propose that these ideas, they are useful for value chains, and then the region, if they want the value chains to be established in the region, maybe the regional government can support interactions. And this is what is happening now in Europe. European Commission supports regions to do more. That was in the first phase, and now the regions should collaborate with each other in Europe. And the next step will be that the regions collaborate internationally between regions. And this is basically where you have benefit from each other. So I think creating a platform in some way is good. And then maybe the most realistic one is that we create one from the existing ones where we have established already connection. Regional people are very slow with fundings and supporting, so it might take a long time. But if we start from our exchange, maybe this webinar is a very good starting point, because then we have exchange and then we have it more continuously. And now when we can do this more online, we don't need to meet and so on, then we can, if we interact that, so then it becomes a platform for exchange, and then there will be more people involved. So if you have interest in such things, I'm certainly interested in from Sweden point of view, because I'm already doing things, having exchange with India. And this is because like in Sweden, we have innovations and ideas, but sometimes we don't have enough driving force for creating these ones. But in India, there are different conditions and you have much more other circumstances than we have. Because I have been, like when I was visiting, I have been to the rural areas, and I was in Allahabad visiting there, and I saw how difficult it is in the rural areas. And there, if we can combine ideas, then we get other motivations. So platforms can be inspired by such things and exchange. So I'm very positive to make any platform for this.
Thank you very much, sir. It is not possible for me to say your contribution in just a few words, but I'm very glad to the attendees, the question raised by the attendees, and also to you, your way of sharing the knowledge through the personal experience, through your personal professional research experience. You shared almost all the things to motivate us for doing research in the field of materials. And we are also happy to know about that how you are eager to in collaboration for India and Sweden relationship. I also very hopeful from the students. So students will grab the opportunity, and in future they will do some interdisciplinary project under your guidance. So I hope from the student side, definitely they will come in after 1 or 2 months with some innovative ideas or some project proposal.
Yes, that's a very good. And if there are like natural links to the activities we have here, then we can propose that these things match naturally. And then from time to time, there are these calls between Sweden and India for fundings and so on. So because on the governmental level, they have decided that there will be more interactions and so on. So it's already something. So if we propose ideas which are naturally matching, they should not be too different, then we can start from there and so on. So such ideas will have higher probability of getting to the next steps, and then we can broaden everything along the way. But just proposing ideas is one good start.
Yeah. So I hope all enjoyed the session, and thank you very much again, and hope we will meet again in the future with some collaboration.
Yes, I'm very, very happy that I have been able to experience this webinar and exchange and so on, because now the online interactions will increase more, and the more comfortable we are with them, then the easier it will be to organize these ones and having the information exchange. So thank you very much for inviting me to be able to support your activity.
Okay. Thank you so much, sir. It was nice. It was a very informative session. Thank you so much. And I would be ending this meeting.
Okay.
Thank you, everyone. Thank you, Sanjay Yadav, sir.
Thank you, madam.
Thank you, Manvendra, sir.
Thank you, everyone.
Thank you. Nice interacting with you. Thank you so much.
Thank you.